Hi everyone, I'm Likhita. Along with my team members Yogesh, Kethan, and project leader Navya, we're here to present our project on WPT using solar panels as a generating source. Wireless transmission was first demonstrated by Nikola Tesla by magnetic resonant coupling, and it has been there for many years. And few applications are toothbrushes, telemetry, satellite communications, and RFID tags. These applications use low amount of power for transfer in the range of microwatts and milliwatts for data transfer. So why do we need wireless power? For near field applications, we don't need wires and it reduces the e-waste. High energy transfer can be achieved through resonant inductive coupling and it is more convenient to use. It has low maintenance cost and it is harmless if field strengths are under safety levels. For far field applications, it can reach remote areas. It is low maintenance cost. We can achieve high efficiency if transmitting and receiving stations are in line of sight and need a grid and substations can be eliminated. So WPT follows few basic laws, and these laws are very well known to everyone, like Ampere circuital law, Biot-Savart's law, and Faraday's law. As you can see, the Biot-Savart's law equation B is equal to mu naught I by 4 pi integral ds into r cap by r square, where mm, where r is the full displacement vector from wire element to point at which the field is being computed. R cap is the unit vector of r, and ds is the linear current element in wire, and mu naught is permeability. So few applications for WPT are biomedical implants, which uses wireless charging, IoT devices, toothbrushes, RFID tags, and many more. Moving over to Ketan.
How to use wireless power transfer for different applications in day-to-day life, and this slide we are seeing that we are using the solar power generated through the solar panels for charging an EV using WPT. So solar energy capturing. Solar energy capturing is a photovoltaic effect. Photons of light ray are absorbed by the semiconductor crystals, which generated significant number of free electrons in the crystal. And here we can see an animation which is showing from the irradiance of sun, the semiconductor is generating the photons in terms of the electrons, which generating the electricity. Tesla Powerwall. Tesla Powerwall is a technology which was developed by Tesla company, and it is the electricity generated in PV panels are stored in power grid system. And here we can see the power grid system and the Tesla batteries which are used to store the electricity. The power can now be transferred wirelessly to car using a system like this. This system shows us the inductive charging, which is used to charge a car using WPT. This is the block diagram of wireless power transfer system. Here we are getting AC mains and AC to DC converter, then DC to RF. It's an amplifier. Then in turns, there we will do an impedance matching, which is used to charge the load. Uh, the impedance matching is done using source resonator, and the frequency should be matched with the device resonator, and in the load will get charged.
The resonance frequency of the specified spiral geometry must be determined. To determine this, studying the spiral resonator impedance is a useful approach to figure out this resonant frequency. Here we can see the simulation run in a MATLAB. Here at a particular frequency, we can see at a particular frequency the impedance is spiked up to 1200. This Lorentz shaped reactance is expected and observed in computed impedance result because the spiral is a magnetic resonator. A power transfer system from spiral to spiral. Here we can see a transmitter TX and a receiver RX make up the entire wireless power transmission system. To maximize the transfer efficiency, use of identical resonators for the transmitter and the receiver is suggested. The wireless power transfer system is represented as a linear array in this diagram. System efficiency as a function of transfer distance. As we know, at a particular distance, the efficient energy transformation occurs. Examining these parameters in this technique, the efficiency of the system changes fast with operating frequency and the coupling strength between the transmitter and receiver resonators. When the system is functioning at its resonant frequency and two resonators are strongly connected, peak efficiency occurs. Critical couple point. When the distance between two resonators is reduced, the coupling between two spiral increases. This is roughly proportional to 1 by d whole cube. As a result, the transfer distance is reduced, the system efficiency improves until it reaches a critical coupled recam. Wireless power transmission. Here we can see a car and how this charging system works. There is a flexibility in XY coordinate and also considering the roof clearance, the car spans all vehicle heights with single design and no moving parts there. There is also a proposition for a moving parts of the charging system in case if the roof clearance is far and the efficiency falls down. Moving over to Navya.
This idea was first proposed by a team of MIT with the concept they came up with the concept of vitricity, and they successfully charged a light bulb which is at a distance of about 2 meters with 60% efficiency using resonant coupling. The further improvements can be made to the project. So the linking of the solar with the WPT can be done is expected to be done in the future. This can be proceeded by modeling the PV arrays and studying the peak times of loads when the vehicles are come to the charging station, at what time the load is maximum. And the MPT, the maximum power tracking, can also be improved by using fuzzy logic. And and there are like ways by which charging can be done. For example, for direct DC charging, we have to use a DC-DC boost converter, and inverters have to be used. So in future, we propose to come up with a design and model the EV charging station through solar panels. Yeah. The references used are given here. Thank you.